I'm going to announce Rein now. Rein is going to speak. And I have to say that today at lunch we convened and came up with a bunch of puns, and I just have a really long list of them. So I'm just going to read through the list just because. Okay. Rein, I don't want to rain on your parade, so I'll rein in my puns. It's raining rain, hallelujah. The weather is nice, let's bring back the rain. Did you save this talk for a rainy day? Stop my reign of terror. I'm going to turn over the reins to rain. Rain, please make it rain. All right, everybody, welcome Rein.
Well, good afternoon, everyone. Can you all hear me okay? Excellent. So before I start, I can beat all of those puns, because I've been living with this name for longer than he has. Before I do that, I'd like to tell a story. I was traveling in Western Europe a few years ago, and I got the chance to go skydiving for the first time. And the reason I'm telling you this story is actually so that I can now say this, that the rain in Spain falls mainly from a plane. Eat it. Okay, so let's talk about math. I can tell from the looks on some of your faces and the attendance at my talk that some of you don't want to talk about math. And that's a problem. And the problem's not actually with any of you. The problem is with math. And not specifically with math, the problem is with the way that we teach math. And I'm going to give you some examples. Actually, first, before I give you some examples, I'm going to give you a statement of the problem, which is, oh good, there we go. So I think we can all agree that we have some vague memories of high school math and maybe college math, but we all have some pretty clear memories of how terrible it was. I can give you some examples of that. How many of you remember high school geometry? How many of you enjoyed high school geometry? How many of you before high school geometry thought that shapes were pretty cool things? How successful was high school geometry in squashing that notion for you forever? Super good. Okay, let's talk about calculus. Isn't how things move really cool? How you can throw a ball and catch it? That's amazing, until you're taught it like this. And what high school calculus manages to do is replace the innate wonder of the mathematics of motion with a mountain of indecipherable symbology that makes no sense to anyone, including the mathematicians. So that's a problem. And what I want to do is I want to present to you what I think is an example of the solution. And that is basically what my talk is today. My talk is sort of a math sandwich, where there's math in the middle, and then on the outside the bread is me talking about how awesome math is. So the reason that I think that math is awesome is because what math actually is, the actual doing of math, is much more like being a field botanist in Costa Rica and going out into the jungle every day, and then one day you discover this amazing Costa Rican jungle hamster. They have those, right? And you observe its behavior for a while, and you discover some really interesting things about the way it lives in its ecosystem, and you then teach it some tricks. And math is way more like that than like what you're taught in school. So I want to hopefully teach you how to do a few tricks with math. So I'm going to start by demonstrating some mathematical creatures for you. This is a triangle. This is a square. All right, that's the math, everyone. Thank you. Thank you for having me. So you can do a thing with a triangle where you take out the middle of a triangle by drawing another triangle. And then you can keep doing that for a while, and a shape begins to appear. Now, you might notice that what we're doing is we're starting with a whole and we are removing parts of it, right? What if we could do the opposite? What if we start with a part and then grow it into the whole? So what if we start with a square, and then what if we duplicate that square at the points of a triangle like this? Now what if we take these 3 squares and we duplicate those at the points of a triangle like this? Now what if we take these and do it again, and then we take these and do it again? So what we're actually building here is the exact same structure in 2 different ways. And it turns out that there is a deep mathematical relationship between the 2 ways that we're doing this. One of those ways is recursive, and the other way is what's called co-recursive. But I'm not going to talk to you about that today. I just like Sierpinski triangles. They're pretty. What I'm going to talk to you about instead is a different kind of mathematical creature, and I'd like to build it up for you, oh, you can do it again, by example. How many of you are familiar with reduce in Ruby? How many of you feel like you know when to use reduce well? How many of you feel like reduce or inject is that thing you reach for when you don't quite want each, but you also don't quite want map? And that's about as far as you've gotten. So I want to give you a way to think about reducing things mathematically. I want to start with summing a list of integers. We can move on to joining a list of strings. We can move on to concatenating a list of lists. So you might notice as we go through this that there's something special about the plus there, about the plus operator when applied to those different things. So let's talk about what's special about plus. The first thing you might notice about plus is that it doesn't matter how you group the pluses, right? You can put the parentheses anywhere you want and get the same result. Now, sometimes you can also switch the terms around and get the same result, but not always, right? So a plus b is not equal to b plus a when they're strings. But it works for a lot of things. It works for a surprisingly large number of things. Okay, close enough. So, really? So let's talk about, in general, this idea of grouping stuff in arbitrary ways and what we can get out of that. That principle, if you remember it from high school math, is called associativity, and it probably was given to you something like this. But I like circles, so we're going to talk about circles. So a set with a binary operation that is associative, like plus and numbers, or plus and strings, or plus and lists, is what's called a semigroup. And you might wonder, why do I care about semigroups? And I'll get to that later. But first, I want to introduce another interesting thing about plus, which is that if you've ever tried to reduce an empty list, you get nil, which is not what you want. And have you ever thought about why you get nil? The reason you get nil is because in Ruby, we can't tell what type of list that is because it's empty. If we knew what type of list that is, we might be able to provide a good default value. But what would be a good default value? If we want to sum, we might want to start with 0. If we want to concatenate strings, so we start with 0 because 0 plus any other number just gives that number back, right? If we want to concatenate strings, we might start with the empty string because it has that same property. The empty string in any other string gives you that string back. With lists, it's the same. So that property, which is your set has some sort of empty element. So when you combine it with other elements, it doesn't change the other element, right? That property is called identity. It might be defined like this, but I think it's clearer to just look at an empty circle and say the empty circle doesn't change the other circle you add it to. And when you take that semigroup with the associative operator and you add identity to it, you get a mathematical creature called a monoid. Now, one of the advantages of knowing what a monoid is that if you want to take a bunch of values and reduce them all together, if those values happen to form a monoid, you're done. That's all you have to do. If they don't, maybe you could spend some time to think about how you might form a monoid out of them. So let's talk about let's actually talk about 2 different things that we can do with monoids. The first is we can use monoids to do some very interesting things. We can also use monoids to think about how we do things. So an example of the first one is the use of monoids for big data processing. We're going to give you two examples. The first one is because we can group operations however we want, we might start by grouping all of the values we've seen so far and then adding another one. And then we might do that again and then add another one. What this means is that monoids let you stream, let you fold over and accumulate over a stream. So if you're looking for doing stream processing and you're looking for a data streaming algorithm or an online algorithm that lets you do streaming, if your data is a monoid, you don't have to look any further. You just use the properties of the monoid and you get exactly what you want. Another example is because you can group these any way you want, I can split them into two, and then I can split those two into two. And once I get down to two elements at the end there, I can join each of those, but I can join them in parallel. Right? I can have 4 cores, 4 threads. Each thread is joining 2 elements, and then I can do that again, and then I can do that again, and what I actually get is, because I can do folds in parallel, I can get log n speedups folding a list of things together. If I can get maximum parallelization, I can get a log n speedup. So that's another advantage of monoids, is that they give you for free the ability to get parallelization out of your reductions and folds. So monoids they sort of form the core of MapReduce. They give you a mathematical way to think about things that you can MapReduce. You try to map a value onto a monoid, and then you use the reduction operation that you get for free because it's a monoid. So let's look at some specific examples of monoids so I can give you an idea of what I'm talking about. We've seen the sum monoid for integers. We've seen the string concatenation monoid. We've seen the list concatenation monoid. But there are some surprising data structures that form monoids that you might not think ought to. So let's look at a few of those. One of the things that we're going to take advantage of here while we look at these is the fact that if you have 2 monoids, you can compose them together and you get a monoid out. And one way you can use that is if you want to take the arithmetic mean of some stream of data or fold over some data in parallel and get the arithmetic mean. I realize this is kind of a trivial example, but a mean is what? A mean is the sum over the count, right? So what you can do is you can use a sum monoid and a count monoid, and then when you're done, you just take the sum and you divide by the count. But that lets you do an arithmetic mean incrementally and in parallel. A slightly less trivial example would be a standard deviation monoid. So what you might do is you might look up some formulas for standard deviations. Here's one. Now, n is the number of elements, so that would be a count. The problem is that sum on the right-hand side, that sigma term there, can't be computed in a single pass. So unfortunately for us, using this equation to compute a standard deviation requires 2 passes, so we can't make it a monoid. So we have to look again, see if we can find a different way to compute a monoid. I'll give you a sec. I like there's nothing easy. So we look for another formula, we find this one. Now this one looks a little bit better. N is again a count. The x's are individual elements, and those sums are, the middle term is a sum of squares, and the right-hand term is a sum that is then squared. So we can do this. We can use a monoid that's composed of a count, a sum of squares, where you just map the number to its square before you sum, and a sum. And that gives us a monoid that we can use as a standard deviation. However, what you end up doing if you use this formula is you take a large number, and then you subtract that from another very large number, and you get back a small number. And this kills the floating points. So you can't really, in fact, if you do this too much, you can come out with a negative standard deviation, which is impossible. So this one doesn't work either. It requires 1 pass, but it doesn't work because of floating point errors. So let's think about another way. So you dig through some of the research, or you just open this book. You flip to page 146, and Donald Knuth has a standard deviation algorithm that works in 1 pass, that doesn't require computations that will accumulate floating point error, And I will leave the implementation of this algorithm as a monoid up to all of you. So, how many of you know what a Bloom filter is? Awesome. How many of you know whether or not a Bloom filter forms a monoid? How many of you want to guess whether or not a Bloom filter forms a monoid? Spoiler alert, it does. So a Bloom filter is a bit vector, right, just a list of bits, and some hashing functions, a set of hashing functions that take an element in a set and turn on some bits in the vector based on where each of the hashes, what value each of the hashes yields. Does that make sense? And then, by the way, if you're not familiar with the Bloom filters, a Bloom filter is a data structure that lets you do approximate set membership, so you sometimes get false positives. But you have very little space usage because it's literally just a bit vector. So you get very, very low space usage, and you also get very good data locality because bits in sequence are very easy to move around your hardware. So it's a really good, it's a really great data structure when you want set membership, kinda. And it's okay if you're sometimes wrong. You can use it for instance, you can use it for caching, where sometimes it's okay if you're not exactly sure whether or not you've cached something. As long as when you're wrong in the way that you can go and get it and perform the computation. Right? Does that make sense? So Bloom filters are used for caching. They're used for a lot of things in data processing. And you might ask yourself, do they form a monoid? Well, what do we need? We need an identity element, right? We need an empty Bloom filter. Well, if a Bloom filter is a list of bits, what's an empty list of bits? Anyone? 0, right? It's a bit vector where all of the bits are 0. So we've got that. We've got identity. Now, we need a binary operation to combine two Bloom filters into a single Bloom filter that associates and preserves identity correctly. Now, if I have two bit vectors, and let me ask you this. Let me rephrase the question. If I want to take a set and another set and join them so that I get all of the members from both sets, what's that called? That's called a union, right? Does anyone know what the bitwise operator is that is equivalent to union? Or, if you want to combine two Bloom filters, you just do a bitwise OR of the bit vectors. And the only requirement is that the Bloom filters have to have the same bit vector length and the same hashing functions. And so by instantiating an empty Bloom filter with a bit vector of zeros and doing a cheap bitwise OR on two vectors, you can combine Bloom filters together. So that means that you can do all of the things we already talked about with Bloom filters because you know they're monoids. You can use them to aggregate data and to stream over data. You can use them in parallel in a MapReduce setting. And all you need to do to prove that that's correct is show that it forms a monoid. So there are some other advanced data structures that are used for big data like count-min-sketch. Is anyone familiar with count-min-sketch? Count-min-sketch is an approximate counting algorithm that I don't understand, but I have seen that it forms a monoid. Also, hyperlog-log forms a monoid. So some surprisingly complex data structures, if you can show that they're monoids, you get a lot for free just for doing that. Does that make sense? So another thing that I want to give you to put in your toolbox is a way to use monoids not to perform computation, but to reason about computation. And in particular, the types of computation I want to talk about are some of the most difficult to reason about, concurrent or distributed computation. So, you might be asking yourself, how can we use a monoid to reason about distributed or concurrent computation? Well, we're going to start with the only mathematical definition I'm going to give you in this entire talk. An alphabet, oh, that is missing some words. Sorry, an alphabet is a non-empty set of letters or symbols, right? So our alphabet is an alphabet, mathematically speaking. We're going to pick a particular alphabet containing the letters A, B, C, D, and E. And furthermore, we're going to say that you join two alphabets together, or sorry, rather you join words formed from that alphabet together using string concatenation. The empty word is just the empty string. And so words formed from an alphabet form a monoid in that way. Does that make sense? Cool. Now we're going to do one other thing, and by the way, this monoid here is called the free monoid for reasons I won't get into, but it shows up everywhere because the free monoid can be transformed into any other monoid, with preserving the structure of the monoid, so preserving identities and preserving composition. So we're going to say that in words from this alphabet, the letters B, C, and D commute, and commuting, of course, means that BC equals CB and so on. Right? So the ordering of those letters together doesn't matter. They're independent, okay? So what we can do is we can form a word from that alphabet, and we can look at all of the different ways we can move letters around and still have it be equivalent up to commutativity. So we can switch C and D, we can switch B and D. Sorry, we can switch it back. We can switch B and C, and we can switch B and D. And if you do that, and you can build up all the permutations of this word that are equal up to the commutativity that we defined. And another way of looking at this is that you can do A first, and then you can do B, C, and D in any order or in parallel. And then you have to do E last. And you might be more familiar with thinking about concurrent computation in terms of dependency graphs. So if we draw arrows from A to B, C, and D, and we draw arrows from B, C, and D to E, we get a dependency graph for the computations that you can build that are valid computations based on the rules about how you have to order these letters. Does that make sense? And it turns out that this monoid with that group of commutative elements is equivalent to dependency graphs. And what that lets you do is that lets you reason about concurrent computation. Rather than using tools from graph theory and topology, you can instead use tools from algebra, because monoids form algebras. So one of the things you can do, and by the way, this monoid that we're talking about is called a trace monoid. And the trace of a word is the set of all words that have an equivalent ordering of letters based on the letters that commute. Does that make sense? So I can reorganize that word into all of these words without changing the semantics of the word in terms of I can switch B's and C's and I can switch C's and D's and so on. One interesting property of the trace monoid is if you look at the size of the trace and you compare it to the size of the entire permutation of that word, so every possible reordering of that word, the ratio of the two is the amount of parallelism you can get out of this ordering of computations. So if the letters are computations, the traces are the ones that are validly ordered based on our rules about how you can order stuff. The size of the trace gives you the amount of parallelism you can get out of those rules about how you can order computation. And what you actually find out is that the larger the trace is, the more your computations commute with each other, the more parallelism you can get. And if anyone's ever done a lot of concurrent or distributed programming, you've probably learned this the hard way, that if you can build your system up out of a lot of independent computations, that order independent computations that commute, you can get a lot of parallelism versus, and this is an interesting thing about the trace monoid, that A that doesn't commute with anything, that E that doesn't commute with anything, are synchronization points. They are where if you were writing a multi-threaded Ruby program, you might want to wrap the computation A with a mutex to make sure that all threads synchronized at that point, right? So if you didn't have a synchronization point at A because you made it a part of the commutative relationship, you can get rid of a mutex. You can make your program more concurrent. So this gives us a way to reason about how much concurrency we can expect from our programs based on how independent the operations are that we're dealing with. How am I in time? Like exactly. So. Okay, hold on. Give me a sec. I'm doing surprisingly well on time. So. Here's what I want to leave you with. And I'm actually going to need my notes for this. What math actually looks like when you're doing it is it looks like discovering some new and interesting creature, finding your own tropical jungle gerbil or whatever, and learning about its behaviors and discovering that it can do things you didn't really think it could do before, or discovering that someone else has already found it out, has already found this thing, and they wrote a paper about it 30 years ago. And the trace monoid stuff is from a paper literally 30 years ago that introduces a calculus called process calculus. And they found out 30 years ago that you can use this thing that you just discovered to do something you never thought it could do. So that's what math feels like to me. And what I want to do is I want to leave you with a couple last thoughts, and maybe have some time for Q&A. I started out the talk with a problem statement, and I want to try to finish with something that might be a solution. I have a couple quotes here for you. First of all, math is about finding patterns, and it's about crafting beautiful and meaningful explanations. And the word crafting here I think is important because math is actually a process of discovery and creativity. When you're actually doing math, you are not applying rules that you were forced to learn by rote, you are creating. You are in an artistic endeavor. And my favorite quote about math of all time is the following one, which I'll read to you. A mathematician, like a painter or a poet, is a maker of patterns. And as humans, we're all makers of patterns. And if his patterns are more permanent than theirs, it's only because they are made with ideas. So the thing that I want to leave you with is that math is art, and that it's beautiful. And so maybe it turns out that math isn't quite what you thought it was, and maybe you can do a little bit more than you thought it could do, and maybe some things that you were interested in, you didn't know were math, but maybe they are. So there's one last thing I'd like to say, and it's not going to be funny, and I'm sorry. I'm not at all surprised that a brief conversation with Jim Weirich was enough to inspire Sandy to give an amazing talk this morning. Because I had a brief conversation with Jim about 4 years ago that inspired me to learn enough to give you this talk today. And I learned another couple of very important lessons from Jim that I'd like to leave you with. The first is that there is an incredible amount of joy to be had in learning new things. And the second is that there's even more joy in sharing them with others. So thank you, Jim, and thank you for letting me share this with you.